So we have explosions. A bullet leaves the muzzle with a velocity of 600 meters per second. You might wonder, why am I doing some scientific notation? I figure I'll review the scientific notation since we're getting towards the end of the year. Ethan is smiling, I know. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil? This is very similar to the Newton's third law rifle shooting video that I showed you just after Christmas. Phil, my friend, is there more than one object in this question? Oh, you said that so authoritatively. And is there a collision in this question? Say no. Is there an explosion, though, in this question? Is there a jeune? This is a job for conservation of momentum. So I'm going to start out the way I always start out. I'm going to write the sum of all the initial momentum has to equal the sum of all the final momentum. You said there's more than one mass. I'm going to label them with letters. You can use A and B. I'm going to use B for bullet and R for rifle, because I think that'll be easier to keep track. I don't think I'd like to let the second mass be mass B, because I would associate that with bullet when it's rifle. I'll get confused. You okay with that? Before we pull the trigger, so imagine the person holding the rifle. Before we pull the trigger, what's moving? The rifle, the bullet, both, or neither? Don't overcomplicate it. Help them out, folks. You know what? I'll ask you the same question. Before we pull the trigger, what's moving? The bullet, the rifle, both, or neither? Very good. So here's the question then for all of you. What's the momentum before we pull the trigger? What's our initial momentum? Exactly as a number? This is a little strange because 0. Bang! We pull the trigger. So what's our final momentum? Still. What's our final momentum as a number exactly? Still. How's that going to work? They're going to be flying in opposite directions. They'll have the same momentum, but one will be positive and one will be negative. So after we pull a trigger, what's moving? The bullet, the rifle, both, or neither? Definitely the bullet, and since they want the rifle velocity, I think both and separate. I'm going to go mass rifle, velocity rifle final, plus mass bullet, velocity bullet final. In explosions, often your initial and your final momentum are 0. Unless the rifle or the bomb or whatever is blowing up was moving ahead of time. And I'll show you an example of that later in the lesson. What am I trying to find, Phil? Which one? There's 2. Okay. What's going to drop down like a domino? I guess the whole left side, which in this case, Mason, is just a 0. How would I get the VR final by itself, folks? How will I get that by itself? Sure, Graydon. Do that? Not yet. Oh, subtract this? Okay, why subtract this? Because we're adding. We do the opposite. So you're telling me it's going to be minus the mass of the bullet, velocity of the bullet, final. We subtract that term over, and then keep going. And then do you mind? I'm going to put VR final over here by itself, because that's where we're used to seeing the thing by itself. You can put it on the right side. I'm not going to freak out, but I usually do that in one step. You'll notice, Jacob, I'm going to get a negative answer, which makes sense. Here's what it's telling you. If the bullet went forward, which it hopefully did, the rifle recoiled in what direction? If the bullet went north, the rifle went. If the bullet went west, the rifle went. Okay, if I gave this as a question on a test, I would probably include an actual compass direction. I would say leaves the muzzle with the velocity of blah, 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 south. Okay, and then I'd probably write the word magnitude and direction. Here, we're just going to get a negative answer, which is telling us in the opposite direction of the bullet, which, from what I recall of those recoil videos, totally makes sense. Let's crunch the numbers. It's going to be 0 minus, Phil, what's the mass of the bullet? That's what MB stands for. 0.06, and is that kilograms? So the units are good. I might on the test at least once, I probably will give you a mass in grams. because we're getting towards the end of the year, and so I can review some basic unit conversion too. Mass of the bullet, 6 times, you know what, 600 is 6 times 10 to the 2. Divided by mass of the rifle, which is 3. You're going to get a negative answer. I can do this in my head. 12? 1.2. No, 12. I think 12. Okay. Yeah, I wrote the negative. I always do the sign first because then I can forget about that and don't have to track it in my brain. 12 meters per second, which is pretty fast. This would go shooting out if you didn't block it with your shoulder and really cinch it up against your shoulder. This is going to move backwards pretty fast. 12 meters per second, that's about Usain Bolt's top speed. Okay, so this is Holland. This is an example of an explosion. And an explosion, often, not always, but often, your initial momentum is 0, which means your final momentum is going to be 0. They have to be going in opposite directions. By the way, I could have made some predictions. They both have the same momentum because the initial momentum was 0. Which one has a heavier mass? The rifle. And so I could have safely said the rifle is going to be going way slower than the bullet. I knew this answer was going to be less than 600. I used to teach canoeing at a summer camp, and I saw this all the time. Spencer is sitting in a canoe, floating on the water next to a dock. He decides to stand up and step out of the canoe and onto the dock. Why does Spencer get wet? So I will mime this. If you look up, here's my canoe. I'm sitting in it right now. Let's say the dock is to my right, to your left. I stand up. What's the momentum of Spencer and the canoe right now? It's really meant to be obvious. Yeah. So what must the momentum be after the explosion? Now, it's not going to be a boom explosion. It's going to be a slow motion step. But what must our momentum be afterwards? Still. Yeah. So if I give myself momentum to my right, which way must the canoe move to keep the momentum 0? Yeah. And I saw this all the time. They would start to step, the canoe would go out, and then they would go splash. Okay? Some of you are smiling. Maybe you've experienced this. So how do you get out of a canoe? You have to introduce an external force. You can't make it a closed system. There's various ways, but usually what I told the kids is I would say, keep your weight low, put your paddles across the canoe for balance, stand up. What's my momentum right now? Still. Do this. What's my momentum? Still. Sit down with your butt on the dock because now there's friction between your backside and the dock. You've introduced an external force now. You've got another force. And now once you do that, you can lift your feet up and out and you're going to be okay. There's all sorts of other ways, but what you don't want to do is just try and step out. Is that all right? Okay. Water is really nice because it's nearly frictionless, and something like a canoe or a paddleboard, they float, a stand-up paddleboard, they float so high on top of the surface of the water, there's so little of them in the water, they're nearly frictionless. They are almost a closed system. Put your pencil down, look up. I'm willing to bet many of you have had an experience where you were playing with a floating toy, an inner tube, a little rubber dinghy or something, and you balanced on it carefully in a lake or in a pool, and you decided you were going to gracefully dive off. And rather than gracefully dive off, you belly flop. Why is that? Well, when you balance on it, what's the momentum of you and the floating toy right now? 0. You want your momentum to go forward. Which way must the inner tube go? Which one has more mass, you or the inner tube? You do. So which one's going to have a bigger velocity, you or the inner tube? Of course, the inner tube's going to have a larger velocity. It's going to shoot out from underneath your feet. And I see a bunch of you smiling. You've tried this when you were a kid, or maybe fairly recently. And you can still try it, but the reason it's so difficult is because of conservation of momentum. I don't want to write a whole paragraph, so let's write this. Momentum of Spencer and canoe equals 0. If Spencer steps right, canoe must move left. Because momentum is conserved. Is that okay? Another one you might have tried is if you've ever been on a skating rink, on an ice rink with a friend, you may have gone face up close to each other, put your hands together, and then pushed each other apart and see how far back, how fast you go back. I see some of you smiling. Let's look at that. Turn the page. A 45-kilogram boy and a 60-kilogram girl are standing in the middle of a frozen pond. The boy gives the girl a push as shown. By the way, since forces come in pairs, that also means that the girl gave the boy a push, same magnitude, because forces come in pairs. And she moves off with a speed of 2.4 meters per second. With what velocity does the boy move off with? Ange, is there more than one object in this question? Say yes. Are they asking me to find a velocity? Yeah. Is this an explosion? A very slow motion one, but technically, yeah. This is a job for conservation of momentum. Here, since they gave me a picture, I'm going to be a bit more careful with direction. This 2.4, Ange, do you want to let that be negative or positive? I don't care. Can you pick for us? Okay, so let's all of us put a negative there. And you know what? I'm going to put a plus in front of the V because I know it's going to be faster. Sorry, it's going to be positive. Who has more mass here, Ange, the boy or the girl? So is the boy going to be moving faster than 2.4, equal to 2.4, or slower than 2.4? What do you folks think? Why faster? They're both going to have the same momentum because my initial... Well, you know what? Is there two objects? Is there an explosion? This is a job for conservation of momentum. So I would probably start by writing that. The total momentum we start with equals the total momentum you finish with. I think I said this last day. You do not have to write that step, but for what it's worth, I'll probably give you a half mark if you do that and leave the rest of the question blank, because at least I'll say, hey, you knew this was a collision or an explosion, and this is conservation of momentum. And I'm going to use G for girl and B for boy. Before the explosion, what's moving? The girl, the boy, both, or neither? Before. Before the explosion, what's moving? The boy, the girl, both, or neither? What's our initial momentum then? Exactly as a number. Yeah, loud and proud, good. Boom, they explode. Well, no. Yay, they push each other off. After the explosion, Ange, looking at the picture, what's moving? I think both and separate. So I'm going to have mass girl, velocity girl, plus mass boy, velocity boy. Momentum and momentum. You okay with that? What are we trying to find, Ange? Velocity. Which one? There's two VFs. Which one of these? Okay. That guy. I guess, again, the 0 is going to drop down like a domino. And then Graydon will minus this over, right? And then divide by the mass. So if I hear you correctly, I think you're telling me that we're going to get the velocity of the boy is going to be 0 minus mass girl, velocity of the girl, all over mass boy. I didn't give us enough room here. I need to redo the spacing, but write small. So the velocity of the boy is going to be 0 minus mass of the girl, 60. Velocity of the girl, and you decided to call it negative. And can you see I'm going to get a minus minus, which is a plus. I am going to get a positive velocity, which I predicted. Divided by 45. So it's going to be positive. I often just put the positive there, Annika, so I don't have to track that myself. You know what? I think I can do this in my head, because if 60 divided by 45 is going to be 4 over 3. 3.2? Double check me, but I think, yes? If I had specifically said magnitude and direction, to the right, or east, or something like that. Here, I think the positive is good enough for now. On a test, I would give you a direction. Is that okay? Cool. Evan, what's B want me to find? Impulse, we're just looking at one mass. Impulse on who? Now, the symbol for impulse, what's another word for impulse, Evan, my friend? So the first thing I write down is change in momentum. And now we're looking at the impulse equation, which is the middle one in that momentum row on your green sheet, yes? Ty, did they give me a force and a time in this question here? I don't think I'm using force times time. Are there different velocities? You know what? I'm going to use the m delta v, except I don't write it that way. I write it as m v final minus m v initial. Oh, Evan, what was the initial velocity of the boy? Oh, that works. So it's going to be 45 times 3.2. I think I can do this in my head. Multiplying by 3.2 is multiplying by 2 5 times. 9, 18, 36, 72. 144? Yeah. Evan, units? Kilogram meters per second. You could also have said Newton seconds. I won't take marks off, but since I use mass and velocity, that's in my brain. If they asked for a direction, the fact that we got a positive answer, we would say to the right. We can do C with no calculator. Erica, what's C want me to find? What's the answer, folks? Too slow. 144, I gotta be fussy. Negative, whatever momentum the boy gained, the girl lost, because that's what the law of conservation of momentum means. If you want the impulse of the girl, she lost 144 kilogram meters per second, or she's going in the negative direction, and since Ange called that the negative direction, we'll be consistent with that. What was the total change in momentum if you add those together? 0. Well, of course, because what momentum were we starting with? 0. So Ange, coming all the way back to you, what momentum must we finish with? Yeah. Hey, now that I have an impulse, I can find an average force. Or if I knew the average force, I could figure out how long this push lasted for. Here, if the push lasted for 0.25 seconds, with what average force did the boy push the girl? Mason, what's the impulse equation that has force in it? So we're in the middle row. First of all, you see you're on your green sheet, yeah? See all the momentum stuff? There's like 3 of them in a row, right? It's one that says P equals mv. I think the impulse equation is right next to that because that's where it has delta P. One of them has forces in it, I hope, I trust. What? Way to let them figure it out, whoever that was. I wanted you to have the aha yourself. I could see you were zoning out. I picked on you on purpose. You're back now? What's this question want me to find? Oh, sorry. Also, I think on your formula sheet, I put a delta in front of the T. Time is always a changing, and I get sloppy and lazy. I tend to abbreviate. What's this question want me to find? How? How will I get the F by itself? Yep. I think I said to you that this was actually how Newton described Newton's second. He didn't write MA. He wrote impulse over time, but it simplifies to MA, so we always introduce it that way. And I'm going to go with, well, they want the impulse on the girl. Did the boy push the girl, the force on the girl? So I'll go negative 144 divided by 0.25. I can do this in my head. Dividing by 0.25, the same as timesing by 4. So it's going to be 400. It's going to be 560, negative 576. Double check me. Yeah. Mason, units, it's a force. Meters per second. By the way, if you blank on that one, think force Newton's laws. Newton's, right? Okay. What's the negative telling me? To the left. So it's consistent. You can also be moving and explode. In this question and in the rifle question, the initial momentum was 0, so the final momentum was 0. Really, in an explosion, your initial and your final momentum are the same. Momentum is conserved. So here's a space capsule, example 4. It starts out as a 4,000 kilogram space capsule, and then it's moving to the right at 120 meters per second when, boom, it explodes. The probe moves off at 280 meters per second. The main capsule, let's make some predictions. Did the probe speed up or slow down after the explosion, looking at the numbers? How fast were we going initially? How fast is the probe going now, if you could try and read my hideous writing? So did it speed up or slow down after the explosion? Sped up. So did the probe gain momentum or lose momentum? Gain momentum. What can you tell me about the main capsule then? Lost momentum, slowed down. I'm going to make a prediction that when we find this, it's going to be less than 120. But here's where it breaks down. It's possible, Maggie, that the explosion could have been so big that this is moving backwards. If I get a negative answer, that's what that means. I don't know. I got to run the numbers. I know it slowed down. I don't know if it actually got forced backwards after the explosion. Did I say explosion? Is there more than one object? You know what this is a job for? Conservation of momentum. So I'm going to start out by writing the total momentum we started with equals the total momentum we finished with. You know what? Let's go with mass A and mass B again. So I'm going to call this mass A. I'm going to call this mass B. I could have called it mass C for capsule, but then it would be P for probe and P for momentum, which might confuse me. So I went with A and B just to keep it simple, stupid. Before the explosion, what's moving? Mass A, mass B? Both or neither? See it? Stuck together or separate? Stuck together, you say. How would I write that? MA plus MB in brackets stuck together times the initial velocity. Boom! The probe explodes. After the explosion, what's moving? Mass A, mass B, both or neither? I think looking at the picture, we would say both separate. Yeah? So we're going to have mass A, velocity A final, there's my final momentum of that, plus mass B, velocity B final. Nat, coming back to you, what did you say this question was wanting us to find? Which is what in this wonderful equation here? I'll give you a hint. It's one of the V's. There's two V finals. Yep, that bad boy right there. Okay, I guess, again, left side's going to drop down like a domino. Bracket MA plus MB, the initial. Then what, Nat? And then divide that whole mess by the mass. And if it's okay with you, Nat, I'm going to put the VA final right there. Good. I'm going to be a little bit lazy. They told me what MA plus MB equals. They told me it's 4,000. So I'm just going to go 4,000. Initial velocity, 120. I've just decided that to the right is positive. So if I get a negative answer, that's going to be to the left. Minus 1,500 times 280, all divided by, what am I going to divide by? 2,500. So be really careful in your substitution. This is why, Ram, I said I want to be lazy, but I want to be organized. You'll see I label whatever I can just so I don't make a silly mistake when I'm putting stuff in. It's preventable. What do you get? I think this will work out evenly, but I could be wrong. What'd you get? 24? Anybody else? 24? In your homework, I didn't care enough to try and make them work out evenly, so you will get decimals in the homework. But here for the notes, I cooked the numbers a little bit. Sorry, grade positive or negative? Okay, so it's still going, that capsule is still going to the right. It didn't slow down so much that it went in reverse. Almost, though, because it was going 120. Now it's going 24. It almost came to a stop. Cool. When you're done yawning, what's B want me to find? Keep reading. Given to the? Okay. Impulse is change in momentum. Am I going to use force and time? Oh. Which one am I going to use? So that we turn it into mv final minus mv initial. By the way, did the probe speed up or slow down? So I'm going to ask you the same question. Did the probe gain momentum or lose momentum? I'm expecting a positive impulse. If they had asked me to find the impulse of the capsule, I would get a negative impulse because it lost momentum. But momentum was conserved. Whatever. In fact, the answer to C is going to be the same as the answer to B. Yes, that's what conservation of momentum tells us. What was the mass? I've scrolled down. Was it 1,500? And 280? Minus 1,500. What was the initial velocity of the probe? Oh, because it was part of the main system? Good. What do you get for the impulse? Two 4 and 4 zeros? Kilogram meters per second. Kiefer, what's the magnitude of the impulse given to the capsule? Yeah. Kilogram meters per second. What was the total change in momentum between both objects? Nothing, because that's what conservation momentum means. Yeah.
Why is it so negative if they're traveling in the same direction?
This one gained momentum.
Okay.
This one.
Okay.
How would we show a negative?
Yeah.
In other words, although they're traveling in the same direction, the momentum change on this guy was definitely backwards because it slowed down.
Yeah.
Is that all right?
Yeah.
Good question. I like this question, but honestly, to make it a little bit easier on a test, I'd include things like east and west or something like that to give you a reference frame. But I'm naturally lazy. To me, negative and positive works for any reference frame quite conveniently, so I tend to fall back on that, right? Mountain climbers, next page. Mountain climbers use nylon safety ropes because they stretch considerably under stress. Why would you want ropes that stretch if you're a mountain climber? Use principles of physics to explain why. Why would increasing time help? Who said that? It came from where that. Why would that help? You're right. Why? I got to remove the word impact with a physics word. What? Oh, this is the impulse equation, because no matter what do we want the final momentum of the climber to be? 0. The initial depends on how far they fell. It's whatever their velocity v final, right when the rope starts to jerk them to a stop is. We're stuck with that, but we don't want to bring them to a stop instantly. We could crack their spine. Now, we also don't want to have them use bungee cords, because if it takes too long, they're going to hit the ground before they come to a stop. And so they use nylon ropes, and they're designed to say, you know what, if I fall, I'll crack a rib, but I'm okay. So, absolutely, Mason is correct. Let's write that without a long paragraph. How about increase time lowers stopping, capital F. Does that work? 5 words. Well, 3 words and 2 letters, even better. Example 6. Anybody here in the fire academy? Anybody here ever use a fire hose? So I have. I worked at a farm for a couple of summers, and we had a full, honest to goodness, full out fire hose that we used. We used it to soak down the gravel parking lot so that dust didn't get on the berries and the crops. And we also used it to clean out the factory. And for the first 5 minutes, I was enough of a child to be saying, wow, I get to play with the fire hose. And then it sucks. Why does conservation of momentum explain why it's so difficult, and it's terribly difficult, for firefighters to hold hoses that are ejecting large amounts of water at high speed? Or in other words, why is it that after 5 minutes of playing with the fire hose, it became a job that I hated and not something fun? Or why would you not want to drink from the fire hose? Pardon me? I want a physics explanation. Yeah.
Because, like, the sigma equation is some.
I think I would answer this in terms of impulse first. Let's just look at the water. Okay? I think you're on the right track. I know where you're going. Here's my hose analog. It's a meter stick. Yeah, human. So here's the hose. In the hose itself, the water's not moving that fast. It doesn't have much mass times velocity. But when it exits the nozzle right there is a tremendous increase in momentum because the velocity increases. There is a tremendous impulse, which means on the water, there is a force times a time. You okay with that? What's applying the force? The hose. Forces come in. So if the hose applies a force times time to the water, what does the water do? It applies a massive force times time on the hose, and it just goes on and on. And so you find, first of all, it's just awkward to hold because there's this constant force acting back on you. It's like someone is pushing on you the whole time. In fact, you have to lean into it, which is an awkward body position to hold for like half an hour. You're on your tiptoes partly because if you're not on your tiptoes, it's going to push you back on your heels, and you don't want to lose control of this thing. It can do some damage. If it hit you in the head when it was moving, it could really do some damage. So you're holding on to it with some pretty intense oomph. But it's a constant backwards force times time. It is. You can also now think about it in terms of momentum. The impulse that the water gains is impulse that the hose loses. But if you just think about it in terms of forces and time, it's not as fun to use the fire hose as you think. It's fun for about 5 minutes. I'm assuming every one of you at least once as a little kid has thought, wow, big hose must be fun. It's really not. I don't want to write a big paragraph. Let's see. Hose applies force times time. If you want to, you can put in brackets impulse. But if you know that force times time is another way to measure impulse, which is another word for change in momentum, you don't need to write that. But to H2O, water. So H2O applies force back on hose, and it gets tiring pretty quick. In fact, often they'll have 2 people on a hose, and the firefighters, if any of you have done the fire academy, they got to be in pretty good shape for many other reasons, but among the reasons is, to man a hose, you got to be in good shape. In fact, fire hoses are used to disperse crowds. If you watch some of the videos from the 1960s civil rights protests in the U.S., you'll see that they use fire hoses on the protesters, and it takes their skin off. Like, there's a lot of force coming out of that water. It's not a pleasant experience. Or, don't drink from a fire hose. Put it in terms that Brendan can follow. Rhetorically? No, I mean, there's good physics there.
Okay, sometimes people ask rhetorical questions and I can't tell.
Okay. Can you tell when I'm asking questions like that? Oh, that was rhetorical. Anyways, here we go. Last one. The diagram below shows 2 pop cans of unequal mass. In fact, one is mass M, and the other one is mass 2M, twice as heavy. An explosive charge is detonated between them. Boom! and the cans fly apart. What can you tell me about their velocities after the explosion? First of all, what was the initial momentum of this system before the explosion? 0. So what must the momentum be afterwards? 0. So the first thing I can tell you is they must be going in opposite directions. Otherwise, how can you have a momentum of 0? Okay with that? Which one's going faster? How much faster? You hear it? So what can be said about their velocities after the explosion? First of all, kind of Captain Obvious, opposite directions. Lighter can is going 2 times faster. This is some of the physics that the RCMP or the FBI or forensics groups would be looking at after a bomb has gone off somewhere. So you're trying to reverse engineer this to figure out where the bomb came from, how much mass there was to begin with, how much energy was stored there to begin with. Sadly, this weekend that has become timely again. It's much more difficult in real life, though, because in real life it's in 3 dimensions, not in a nice straight line, 1 dimension, but with software, you're using conservation of momentum and conservation of energy to reverse engineer the whole process and figure out where it all came from and how much mass there was to begin with. It says using principles of physics explain your answer, but is that okay in terms of the momentum is conserved? Okay. Okay. What's your homework? We crossed out some questions. So first of all, 1 is good. Number 2, if you want to take a look at number 2, I was trying really hard to use pictures. So if you look, there's a whole bunch of collisions. In diagram A, the fact that they're touching means after the collision they stuck together. And before, since the 13 doesn't have an arrow on it, how fast is the 13 kilogram mass traveling? 0. So how much momentum does it have? 0. So before the collision, what's moving? Mass 1 or mass A. Wham, they collide, stuck together. I stole this from the internet. I liked it because it kind of had almost every possible way to mix and match collisions. So 2 is good. 3, 4, 5, 6, you can cross out number 7. Eight is good. 9 is good. 10 is good. You can cross out 11. 12 is good. You can cross out 13. 12 is nasty. It's harder than I'm going to ask you, but we're getting towards the end of the year. It's good review. 12A is absolutely fair game because 12A says find the final speed of both cars after the collision. 12B wants you to find the distance they traveled before skidding to a stop. Your hint there is it's a job for a free body diagram. You're going to need to find the acceleration. You know V final is 0. V initial is your answer from A, and you can find D. I think using VF squared equals VI squared plus 2AD. And then C, find the impact force on both cars. Once you know A, if you know the mass, you can go MA. Figure that out. Okay? You have the remainder of class, my angels.